What if everything we thought we knew about the universe's expansion was actually discovered centuries ago, then lost to time, hidden in ancient manuscripts, tucked away in forgotten libraries, lie 24 mathematical masterpieces that predicted the cosmos was stretching outward long before Edwin Hubble's telescope ever captured the evidence. These aren't just dusty old papers, they're cosmic prophecies, penned by brilliant minds who saw the universe's grand design with nothing but ink, intuition, and sheer genius. And here's what's truly astonishing. Their calculations weren't just close, they were right. Think about that for a moment. While modern science credits 20th century astronomers with uncovering the expansion of the universe, these long-lost texts reveal a startling truth. Someone, somewhere, in a world without satellites or supercomputers, had already mapped the heavens' secrets. Who were these visionaries? How did they grasp such profound truths without the tools we take for granted? And most haunting of all, why were their discoveries erased from history? This isn't just a story about numbers. It's a mystery that shakes the foundation of how we measure progress itself. So let's embark on a journey through time, across continents, and into the minds of history's unsung geniuses. Together, we'll decipher their cryptic equations, unravel the threads of their forgotten legacies, and uncover how the cosmos whispered its secrets to those who knew how to listen. By the end, you won't just see the universe differently, you'll see humanity differently, because if these masterpieces teach us anything, it's this: the truth is out there. And sometimes it's been waiting for us all along. Picture a world without telescopes, without satellites, where the night sky was a mystery waiting to be unlocked by nothing more than human curiosity and a steady hand. That's where our story truly begins, with the brilliant minds who dared to decode the universe using nothing but ink and intuition. Take Alhazen, an 11th century scholar from Baskara, whose experiments with light and shadow laid the groundwork for modern optics. While his peers saw the stars as fixed points, he theorized that space might not be as static as it seemed. Then there's Baskara, the 12th century Indian mathematician who calculated planetary motion with such precision that his equations, centuries later, would eerily align with the laws of celestial expansion. And let's not forget Nicole Osmie, a French bishop and scientist who, in the 1300s, sketched diagrams suggesting the heavens were in motion, long before anyone had the tools to prove it. What connects these thinkers isn't just their genius, but their isolation. They worked in candlelit scriptoriums, in courtyards under open skies, far from the collaborative labs of modern science. Yet somehow they glimpsed truths that would take the rest of humanity hundreds of years to rediscover. Their tools were simple: compasses, astrolabes, and the relentless power of observation. But their conclusions, monumental. Alhazen's treatises on light refraction hinted at a universe where space itself could bend. Baskara's orbital calculations suggested planets weren't just moving, they were drifting apart. And Osmie's sketches, dismissed as heresy in his time, now read like prophetic blueprints of an expanding cosmos. The tragedy: their work often vanished into the shadows of history, suppressed by dogma, lost to war, or simply forgotten in the chaos of time. Imagine if their ideas had flourished, how much sooner might we have unraveled the universe's secrets. Their stories aren't just footnotes in the history of science. They're proof that brilliance isn't bound by era or technology. Sometimes all it takes is a curious mind, a steady hand, and the courage to see beyond the limits of the known. Deep in the archives of Cairo's ancient libraries, buried beneath layers of dust and time, lies a manuscript that changed everything: Alhazen's Book of Optics. Written in the 11th century, this wasn't just a study of light, it was a silent revolution. While his contemporaries saw the heavens as an unchanging tapestry, Alhazen dared to question it. With nothing more than a quill and his own meticulous observations, he sketched geometric models showing how light from distant stars might behave over vast distances. Here's the astonishing part. His calculations suggested that if stars moved, their light would shift in ways we could measure, a concept eerily similar to what we now call redshift, the very phenomenon that proves our universe is expanding. But how, without telescopes or spectrometers, Alhazen relied on something even more powerful, the laws of geometry and the behavior of light itself. He noticed how light bent through different mediums like water or glass and wondered, could space itself act as a lens distorting the light of faraway objects? His experiments with reflection and refraction led him to a radical idea. The cosmos might not be static. It could be breathing, shifting, changing. And if that were true, then the light reaching us from the stars would carry clues about their motion. This wasn't just speculation. It was a blueprint for understanding cosmic expansion, written 800 years before Hubble pointed his telescope at the heavens. Yet history nearly erased his breakthrough. Alhazen's work was copied, translated, and scattered across empires, often misunderstood or dismissed as philosophical musings. It wasn't until the 20th century that scientists revisiting his manuscripts realized the depth of his insight. Those geometric diagrams, they weren't just abstract art. They were equations in disguise, describing how light's wavelength could stretch as space itself expanded. Today, astrophysicists marvel at how closely his models mirror our modern understanding of redshift. But the real question isn't just how Alhazen got it right. It's why his ideas had to wait a millennium to be proven. Was it the limits of his tools or the limits of his world's imagination? Alhazen's story teaches us something profound. Genius doesn't wait for technology to catch up. Sometimes it's the sheer audacity to ask, what if that changes everything? And in the quiet of his candlelit study, with only parchment and patience, one man saw the universe for what it truly was, not a fixed stage, but a living, growing thing. His masterpiece wasn't just ahead of its time, it was waiting for ours. Long before calculus had a name, centuries before Newton penned his laws of motion, a mathematician in 12th century India was quietly rewriting the rules of the cosmos. Baskara, a scholar whose name means the enlightened one, didn't just study the stars, he spoke their language. In his monumental work, the Siddhanta Shiromani, he laid out equations so precise they could predict planetary positions down to the minute. But here's what's truly staggering. Buried in those calculations was a hint of something far grander. Baskara wasn't just tracking planets. He was unwittingly mapping an expanding universe. Take his analysis of lunar motion. While his contemporaries saw the moon's path as fixed, Baskara's calculations revealed tiny discrepancies, shifts that couldn't be explained by gravity alone. His solution, a radical tweak to the geometry of space itself. In poetic Sanskrit verses, he described celestial bodies as drifting like leaves on a river, their distances subtly increasing over time. Today, we'd call that cosmic expansion, but without the vocabulary of modern physics, Baskara framed it as a divine dance, a slow unfurling of the heavens. His palm leaf manuscripts, painstakingly inked by hand, even included diagrams showing orbits as spirals, not perfect circles, as if space itself were stretching beneath them. Yet for all his brilliance, Baskara's work met a fate worse than obscurity, mistranslation. Later scholars, fixated on astrology, dismissed his math as mystical numerology. His spiraling orbits were recast as symbolic mandalas, his precise equations reduced to horoscopic tools. It wasn't until the 1900s, when historians revisited his original texts, that the truth emerged. Those spirals weren't art, they were calculus in disguise, graphing the gradual separation of celestial bodies. And those divine dances, they matched almost perfectly with what we now know as Hubble's law, the cornerstone of cosmic expansion. What makes Baskara's story so haunting isn't just the accuracy of his predictions. It's the reminder that discovery doesn't always march forward in a straight line. Sometimes it loops back on itself, leaving truths to gather dust until the world is ready to see them. Had his peers grasped the weight of his work, might we have unlocked the universe's secrets centuries earlier? Or was the very act of preservation, those fragile palm leaves surviving monsoons and invasions, its own kind of miracle? Baskara's legacy isn't just in the numbers he left behind. It's in the quiet proof that genius transcends time, and that the cosmos whispers its secrets to those patient enough to listen, even if the rest of the world isn't ready to hear. In the flickering candlelight of a 14th century French monastery, a man named Nicole Osmie was quietly tearing apart the cosmos as Europe knew it. While his contemporaries clung to Aristotle's vision of a perfect, unchanging universe, a celestial sphere with Earth at its center, Osmie dared to sketch something radical, an infinite void stretching endlessly in all directions where matter drifted apart like smoke on the wind. His manuscript, The Book of the Heavens and the World, wasn't just heretical, it was a time capsule of genius buried for centuries, because what Osmie described wasn't just a philosophical musing. It was dark energy 800 years before science had a name for it. How did a medieval scholar without telescopes or particle accelerators grasp such a modern idea? Osmie's tools were deceptively simple: logic, geometry, and an obsession with motion. He noticed that if the universe had a center, objects should behave differently depending on their distance from it, yet the heavens showed no such pattern. Stars moved with the same regularity whether they were near or far. His conclusion: there was no center. Space had no edges, no fixed points, just an endless expanse where matter was forever dispersing. Sound familiar? Today, we call that the accelerating expansion of the universe, driven by the mysterious force of dark energy. But Osmie framed it in terms even a peasant could understand. Imagine a firework bursting in the night, he wrote. The sparks fly outward, never returning, always spreading. So too does God's creation unfold. The church, unsurprisingly, wasn't thrilled. Osmie's ideas threatened the very order of the medieval worldview, where heaven and earth were rigidly separated. His manuscripts were locked away, labeled too dangerous for public eyes. Yet fragments survived, smuggled out by sympathetic monks or hidden in plain sight as marginalia in less controversial texts. For centuries, they gathered dust until modern historians, piecing together the puzzle, realized Osmie hadn't just challenged Aristotle. He'd anticipated Einstein, Hubble, and the entire framework of modern cosmology. His infinite universe wasn't a metaphor, it was a prediction. What's most haunting about Osmie's story isn't just the accuracy of his vision, it's the fragility of truth itself. Had his work been celebrated instead of suppressed, might humanity have grasped the nature of the cosmos centuries earlier? Or was the world simply not ready to hear that the universe was infinite, centerless, and alive with motion? Osmie's legacy reminds us that progress isn't a straight line. Sometimes it's a whisper in the dark, waiting for the right moment to be heard. And sometimes the future arrives far too soon, only to be forgotten until time finally catches up. History has a cruel way of treating its greatest treasures not with reverence but with indifference. Imagine a single manuscript, its pages filled with revelations about the cosmos, resting on a shelf in some forgotten library. Then comes the siege, the fire, the flood. In an instant, centuries of insight vanish into smoke or dissolve into mud. This wasn't the exception for these mathematical masterpieces, it was the rule. Take the great library of Alexandria, where countless works on astronomy and geometry were reduced to ashes. But even when texts survived the flames, they faced subtler threats, the quiet erosion of translation. A 9th century Arabic manuscript on celestial mechanics might be copied by a Latin scribe who didn't understand the math, turning precise diagrams into vague sketches. A Sanskrit verse describing orbital motion could be condensed into a poetic metaphor, its equations lost in the shorthand of a hurried scholar. Then there's the irony of preservation itself. Some of these works only endured because they were repurposed, their original intent erased. Astronomical charts became wallpaper for noblemen's homes, their grid lines admired as decorative patterns. Complex equations were scribbled in the margins of prayer books, dismissed as doodles. One Persian scholar's treatise on the motion of galaxies was literally cut apart, its pages used to bind a cookbook. The very act of survival sometimes meant distortion, like a game of telephone across centuries. A 12th century Andalusian text predicting cosmic expansion was translated into Hebrew, then Italian, then French, each version smoothing away its most radical ideas until it read like a harmless philosophical musing. But the real tragedy isn't just what was lost, it's what we'll never know was lost. For every manuscript that survived in fragments, how many vanished completely? When Mongol armies sacked Baghdad in 1258, they threw the contents of the House of Wisdom into the Tigris River, turning its ink into a black stain on the water. Historians still wonder what groundbreaking theories drowned that day, and what about the works that were deliberately destroyed? The Catholic Church's index of forbidden books included dozens of scientific texts deemed too dangerous for public reading. Some were burned, others were locked away in vaults, their pages slowly eaten by damp and worms. This isn't just a story about fragile parchment or fading ink. It's about the fragility of truth itself. Knowledge isn't some unshakable monument, it's a whisper passed from one generation to the next, easily drowned out by the noise of history. Those 24 lost masterpieces, they're not just relics, they're warnings, because every time we assume our understanding of the universe is complete, we risk repeating the same mistake, forgetting how much has already been forgotten. The question isn't just what those texts contained, it's what else might be out there, still waiting in some undiscovered archive, or worse, gone forever, leaving us to rediscover the wheel century after century. By the 19th century, something extraordinary was stirring in the halls of academia, a quiet revolution of rediscovery. Scholars, armed with lanterns and magnifying glasses, began peeling back the layers of time, unearthing manuscripts that had been dismissed as relics of a pre-scientific age. Orientalists like William Jones pored over crumbling Sanskrit texts in Calcutta, while historians in Paris and Oxford combed through medieval archives, their fingers tracing the faint ink of forgotten genius. What they found wasn't just historical curiosity, it was a seismic challenge to the very timeline of scientific progress. Take Henry Corbin, a French philosopher who stumbled upon a 12th century Persian treatise in an Istanbul library. As he deciphered its intricate diagrams, his hands trembled. Here, in elegant Arabic calligraphy, was a detailed model of celestial motion that mirrored modern theories of an expanding cosmos. But when he presented his findings to the Royal Society, the room erupted in skepticism. How could a medieval scholar without calculus or telescopes have deduced what Einstein's equations would only confirm centuries later? The establishment's resistance was fierce. Science, after all, was supposed to be a linear march forward, not a circle leading back to the past. Yet the evidence kept mounting. Pierre Duhem, a physicist turned historian, made an even more startling claim after studying Nicole Osmie's neglected manuscripts. He argued that the medieval bishops' theories of infinite space weren't just philosophical musings. They were mathematical predictions, eerily close to Friedman's solutions for an expanding universe. Duhem's peers scoffed, but then came the clincher. A team in Berlin uncovered Bhaskara's original palm leaf manuscripts, buried under centuries of annotations. His spiral orbits, once dismissed as poetic metaphor, were now recognized as calculus in disguise, graphing the gradual separation of celestial bodies. The irony was undeniable. These 19th century scholars, trained in the rigid paradigms of Newton and Laplace, found themselves dismantling the very narrative they'd been taught. Science wasn't a torch passed neatly from one European genius to the next. It was a mosaic, its pieces scattered across continents and centuries, waiting to be reassembled. And with each rediscovered text, the mosaic grew clearer, revealing a truth far more humbling than anyone had anticipated. The universe's greatest secrets hadn't been unlocked by modern telescopes alone. They'd been whispered centuries earlier by minds working in the quiet corners of history. The only question left was how many more whispers had been lost to time, and what else we might still find if only we knew where to look. The true marvel of these ancient texts isn't just their ideas, it's the language they spoke, mathematics, not as we know it today with its standardized symbols and notation, but as a living, evolving dialect shaped by the hands and minds of scholars working in isolation across continents. Take that Persian manuscript describing a breathing cosmos. At first glance, its pages seem filled with ornate geometric patterns, the kind you might find in a medieval art gallery. But look closer, those interlacing circles and spirals, they're equations in disguise, geometric series calculating the exponential stretching of space, a concept we now call cosmic inflation. The scribe didn't have the vocabulary of modern physics, so he encoded his insight in the universal language of shapes, each curve a silent testament to the universe's hidden rhythm. Then there's the Ming Dynasty text, its brittle pages covered in brushstrokes that look more like poetry than science. Yet nestled between lines about celestial harmonies are differential equations, their ink faded but their logic intact. Using nothing but abacus beads and observational data, the astronomer who penned them approximated the rate of cosmic expansion with startling accuracy. How? By tracking the slow drift of stars over generations, noting how their positions subtly shifted not just across the sky, but away from one another. His calculations, expressed in the fluid strokes of Chinese calculus, didn't just predict Hubble's law. They framed it as a natural consequence of cosmic balance, a dance of yin and yang on the grandest scale. Deciphering these works is like cracking a code where the cipher changes with every page. A 15th century Venetian manuscript might use musical notation to represent orbital frequencies, with quavers and clefs standing in for mathematical operators. A Mayan codex could depict planetary motion as a series of glyphs, each symbol a nested equation counting the days until a star's light stretched into redshift. Modern scholars armed with supercomputers have spent years reconstructing these lost methodologies, peeling back layer after layer of abstraction to reveal the rigor beneath. What they've found appends everything we thought we knew about the history of science. These weren't hunches or lucky guesses. They were systematic, repeatable, testable theories expressed in the only vocabulary their creators had. And that's what makes their disappearance so haunting. When knowledge is locked away in esoteric notation, it becomes vulnerable. A single mistranslation, a curve misread as decoration, a glyph misinterpreted as myth can erase centuries of insight. The Persian Breathing Cosmos manuscript nearly suffered this fate, dismissed as Sufi mysticism until a 21st century physicist recognized its geometric series as a mathematical model of inflation. The Ming equations were almost lost to time because their notation resembled classical poetry, their numbers hiding in plain sight. These texts force us to confront an uncomfortable truth. Progress isn't just about discovery. It's about transmission. The brilliance of these thinkers wasn't extinguished by lack of imagination. It was shattered by the fragility of the vessels meant to carry it forward. So the next time you hear about a groundbreaking modern theory, dark energy, multiverses, quantum foam, pause for a moment. Somewhere, in some forgotten archive, there may already be a page waiting to be read anew. A page where ink and intuition once converged to map the cosmos, only to be shelved, silenced, or scribbled over. The past isn't just prologue, sometimes it's the most advanced chapter of all. Religion and philosophy have always walked a razor's edge when it comes to scientific discovery, sometimes guarding knowledge like sacred flame, other times smothering it under doctrine. Consider the House of Wisdom in 9th century Baghdad, where Islamic scholars like Al-Khwarizmi refined algebra while mapping the heavens, all within the framework of Quranic cosmology. Their manuscripts didn't just preserve Greek and Indian astronomy, they advanced it, proving faith and reason could coexist. Yet even here, boundaries existed. When certain calculations threatened to contradict scripture, scholars often cloaked their findings in metaphor, describing celestial mechanics as the unfolding of divine will, rather than outright physical laws. This wasn't deception, it was survival. A scholar's work could flourish if framed as glorifying God's creation, but risk destruction if labeled heresy. Across the Mediterranean, the Catholic Church's grip on cosmology created a different kind of tension. Nicole Osmie's infinite universe theory might have revolutionized science in the 1300s had it not been buried under layers of ecclesiastical approval. Clerics like Osmie himself, who served as bishops, faced an impossible choice: push too hard, and their work would vanish into the index of forbidden books. Too soft, and the ideas lost their cutting edge. The result, a dance of coded language. Osmie's sketches of an expanding cosmos were presented as meditations on God's boundless nature, while his mathematical proofs hid in plain sight as commentary on Aristotle. For every text that survived this way, countless others were lost, their radical truths too naked for the senses' eyes. Yet spirituality wasn't just a barrier, it was often the very engine of discovery. Baskara saw his celestial equations as hymns to Hindu deities, each planetary motion a stanza in the universe's sacred song. Jesuit astronomers in China, armed with telescopes but bound by Vatican doctrine, meticulously recorded data that later confirmed cosmic expansion, all while believing they were tracing the fingerprint of the Creator. Even Isaac Newton, who rediscovered much of Baskara's calculus centuries later, spent more time decoding biblical prophecies than writing the Principia Mathematica. The irony is profound. The same fervor that drove some to suppress unconventional ideas also drove others to seek them, convinced that unraveling the cosmos was the ultimate act of devotion. This duality explains why so many masterpieces vanished or survived in fragments. A Persian astronomer's treatise on an expanding universe might be saved by a caliph who saw it as proof of Allah's infinite power, only to be burned centuries later by fundamentalists who deemed it blasphemy. A Mayan codex predicting galactic drift could be preserved as ritual calendar, then destroyed by conquistadors who feared its pagan science. The fragility of these texts wasn't just about fragile parchment, it was about the precarious balance between revelation and orthodoxy. What modern readers often miss is how much we owe to those who navigated this tightrope. Without the monks who secretly copied Osmie's work, or the Sufi scribes who embedded cosmic truths in poetry, these ideas might have been erased entirely. Their legacy isn't just in the equations they left behind, but in the reminder that knowledge never travels in a straight line. Sometimes it slips through the cracks of dogma, disguised as something else, waiting for a world ready to see it for what it truly is. Hidden among the vibrant glyphs and celestial charts of the Dresden Codex lies a numerical puzzle that's only now beginning to unravel. This 13th century Mayan manuscript, best known for its precise Venus tables, contains something far more extraordinary, a series of mysterious sequences that modern mathematicians have identified as equations describing cosmic scaling. Picture this: while European scholars were still debating whether Earth was flat, Mayan astronomers in the jungles of Yucatan were tracking not just planetary motion, but the subtle stretching of space itself. Their tool, a Vigesimal numbering system base 20 instead of our base 10, that turned simple dots and bars into a sophisticated language for modeling the universe's expansion. What makes these calculations so revolutionary is how they mirror discoveries made oceans and centuries apart. Like Baskara's spiraling orbits or Osmie's infinite void, the Mayan scribes framed cosmic expansion through the lens of their own worldview, cyclical time. To them, the universe wasn't just expanding, it was breathing, inhaling and exhaling across vast epochs they called world ages. Their codex's numerical sequences, once dismissed as ritual countdowns, are now recognized as logarithmic progressions charting how celestial distances increase over these cycles. One particular table, previously thought to predict eclipses, actually plots the growing separation of stars with eerie accuracy, using nothing but bark paper and a system of mathematics so advanced, early translators mistook it for astrology. The real breakthrough came when researchers realized the codex's long count calendar wasn't just tracking days. It was a cosmic ruler. By correlating its intervals with observed shifts in planetary positions, the Mayans had essentially derived an ancient version of Hubble's constant, the rate at which the universe expands. Their Vigesimal math allowed them to express fractional cosmic scales with precision that decimal systems would struggle to match. Imagine dividing a single day into 20 kin, each kin into 20 yuanal, and so on, a cascading fractions game that gave them resolution fine enough to detect astronomical drift over generations. Yet the most haunting parallel lies in how this knowledge was nearly lost. When Spanish conquistadors burned Mayan libraries in the 16th century, the Dresden Codex survived by sheer luck, one of only 4 pre-Columbian manuscripts to endure. Its equations, painstakingly painted with cochineal dye and Maya blue, faded into obscurity until 20th century scholars began decoding its true significance. Now, as astrophysicists compare its tables to modern redshift data, they're finding unsettling consistencies. Those ritual numbers align suspiciously well with contemporary calculations of cosmic acceleration. This isn't just about one culture's brilliance. It's about a pattern repeating across continents, from Baskara's India to Osmie's France to these Mayan scribes, each arriving at the same staggering truth through different intellectual paths. The Dresden Codex forces us to ask, was cosmic expansion somehow more visible to ancient astronomers, unclouded by light pollution or the assumptions of modern physics? Or is there something fundamental about human curiosity that, given enough time and observation, inevitably leads to the universe's deepest secrets? The answer might still be hiding in those faded glyphs, waiting for the right eyes to see them anew. The Silk Road wasn't just a highway for spices and silk. It was a living, breathing network of ideas where the most precious cargo wasn't gold but knowledge. Picture a Persian merchant in a bustling Samarkand caravanserai, unrolling a star chart next to a Chinese alchemist scroll. The numerals on one page were Arabic, the calculations inked in Sanskrit, the diagrams labeled in Greek. This wasn't just trade, it was the world's first internet, a slow-motion exchange of cosmic insights that spanned deserts and dynasties. And somewhere in that chaos of languages and cultures, fragments of the universe's deepest secrets were being passed hand to hand, often without anyone realizing their significance. Take the case of the Zij-i-Ilkhani, a 13th century Persian astronomical treatise that made its way to Beijing. Its pages contained tables predicting planetary motion with uncanny precision, but tucked between the rows of data was something stranger, a note about the thinning of celestial light over time. To its original author, Nasir al-Din al-Tusi, this might have been a passing observation, but when the text reached Chinese mathematician Guo Shaojing, he saw a pattern. By cross-referencing it with centuries of imperial sky records, he deduced that stars weren't just moving, they were fading, as if space itself were diluting their light. Today, we'd call that redshift. Back then, it was a footnote in a manuscript that only survived because a Mongol Khan funded its translation. Yet for every breakthrough that traveled intact, a dozen others fractured like pottery on the road's rough paths. A Byzantine monk might copy Baskara's spiral orbits into his notebook, but without the underlying calculus, they became mere decoration. A Tibetan translator could misinterpret Alhazen's light refraction as a metaphor for spiritual enlightenment. The most tragic losses weren't from malice or suppression, but simple miscommunication, like the Baghdad scholar who rewrote a Gupta-era Indian text on cosmic expansion, smoothing its radical math into poetic verse to suit his patron's tastes. Centuries later, when historians found the watered-down version, they dismissed it as mythology, unaware that the original had been left to crumble in a monsoon-soaked Bengal library. What's astonishing isn't just how far these ideas traveled, but how they transformed along the way. Nicole Osmie's sketches of an infinite universe reached Islamic Spain via Jewish traders, where they inspired Ibn Rushd to theorize about multiple heavens, a concept that later circled back to influence Copernicus. The Maya's Videsimal calculations, carried across the Pacific by Austronesian sailors, resurfaced in Javanese navigational charts that Portuguese explorers eventually brought to Europe. This wasn't a straight line of progress. It was a sprawling, messy web where breakthroughs could cross continents only to stall for centuries, waiting for the right mind to reassemble them. The Silk Road's greatest lesson might be this: knowledge is never truly lost. It's misplaced, repurposed, or buried in translation, but it lingers sometimes in the unlikeliest places. A throwaway line in a merchant's ledger about the stretching sky could hold the key to a cosmic mystery. A child's doodle in the margin of a caravan manifest might be the last trace of a genius's unreadable handwriting. These fragments remind us that discovery isn't a solitary act. It's a chorus of voices across time, each adding a note to a song we're only now beginning to hear in full. And somewhere in that chorus, between the lines of half-remembered texts and half-understood diagrams, the universe keeps whispering its oldest secrets. When we think of medieval universities, images of robed monks debating scripture might come to mind. But behind those cloistered walls, something far more revolutionary was unfolding. Take Oxford in the 1300s, where scholars pored over candlelit manuscripts not just of theology, but of geometry, optics, and the very nature of space itself. Robert Grosseteste, a humble English bishop turned Oxford chancellor, penned a treatise titled De Luce on Light. that dared to propose the universe began with an explosive pulse of illumination, scattering matter outward in an ever-expanding sphere. Sound familiar? It's a conceptual cousin to the Big Bang Theory, written 700 years before Hubble, and Grosseteste wasn't working in isolation. His ideas drew directly from Arabic texts smuggled into Europe through Sicily, where Muslim and Jewish scholars had preserved and expanded Greek cosmology. The classrooms of Bologna and Paris buzzed with equally radical speculations. Student notebooks from the era, preserved in remarkable detail, reveal feverish diagrams of concentric spheres, not as static layers, but as dynamic shells stretching over time. One marginal doodle from a 14th century Padua lecture shows stars drifting apart like crumbs on rising dough, a metaphor that would later echo in modern descriptions of cosmic expansion. What's astonishing isn't just the ideas themselves, but how openly they circulated. While the Church kept a watchful eye, these universities operated under a fragile but real intellectual freedom. Professors could argue that space might be infinite, so long as they framed it as pondering God's boundless creation. A clever scholar could hide groundbreaking math in commentary on Aristotle, disguising calculus as philosophical musing. The real surprise, how much of this ferment was collaborative. When Grosseteste's successor, Roger Bacon, hypothesized that light from distant stars might carry clues about the universe's structure, he cited not just Latin texts but Persian star charts and Hebrew translations of Indian astronomy. These weren't isolated geniuses, they were nodes in a vast, if uneven, network of knowledge. Even the rigid scholastic method, often dismissed as pedantic, had a hidden virtue. It forced thinkers to articulate their theories with razor precision, building arguments that could withstand theological scrutiny while smuggling in radical physics. Yet for all their brilliance, these scholars faced a bottleneck their predecessors hadn't. The printing press was still a century away. Ideas that might have spread like wildfire instead trickled through Europe in painstaking hand-copied manuscripts, vulnerable to error, censorship, or simple decay. A student's notebook from Krakow might contain a revolutionary insight about celestial motion, only to be used as kindling during a harsh winter. The fragility of this system makes the surviving fragments all the more precious, like the battered parchment from Sorbonne's archives, where an anonymous scribe calculated the rate of heaven's unfolding, using geometry borrowed from Cairo's astronomers. His numbers were off by modern standards, but his logic was startlingly sound. If stars were drifting apart, their trajectories should follow precise angular relationships. What medieval universities prove is that curiosity can flourish even in the shadow of dogma. The same institutions that taught theology also nurtured the first inklings of astrophysics, their lecture halls echoing with debates that would one day reshape our understanding of the cosmos. The real tragedy isn't that these ideas were suppressed. It's that so many were forgotten, not by design but by the slow erosion of time. When we dismiss the Middle Ages as a dark period for science, we overlook the quiet brilliance of those who kept the flame of inquiry alive, waiting for the world to catch up to their vision. Their chalkboards may have been slate, their telescopes imaginary, but their insights, as we're finally discovering, were anything but. Gutenberg's printing press promised to illuminate the world with knowledge, but like every revolution, it cast shadows too. On one hand, the ability to mass-produce books meant ideas could spread faster and farther than ever before. On the other, it created an invisible filter, a gatekeeper deciding which truths were worth preserving and which would crumble into dust. Think of it this way: when printing a book required carving each page by hand, scribes chose carefully, often copying whatever rare manuscripts they could find. But with movable type, the equation flipped. Printers needed to turn a profit, so they prioritized what would sell: Bibles, legal texts, popular philosophy. The obscure, the unconventional, the mathematically daring, those were left to languish in forgotten corners, their pages growing brittle while the world moved on. Consider the fate of Nicole Osmie's infinite universe theory. His original 14th century manuscript, painstakingly hand-copied by monks, survived in a handful of fragile copies. But when the printing press arrived a century later, no publisher dared touch it. Too radical, too niche, too risky. Meanwhile, Aristotle's geocentric views, already centuries out of date, rolled off the presses by the thousands, reinforcing old errors simply because they were familiar. This wasn't malice, it was market forces. The same mechanism that made knowledge accessible also flattened it, favoring consensus over curiosity. And then there's the problem of abridgment. Many scientific works that did make it into print were stripped down, their most challenging ideas softened or removed. A Persian astronomer's treatise on cosmic expansion might be translated, but without its complex diagrams reduced to a vague description of the heavens' grandeur. Mathematical notations, especially those from non-European traditions, often fared worst. Baskara's spiraling orbits, precise in his original palm leaf manuscripts, became mere decorative flourishes in printed editions, their calculations lost in translation. The printing press didn't just preserve knowledge, it sanitized it, smoothing away the rough edges that made these ideas revolutionary. Yet amid this winnowing, glimmers of hope persisted. Scholars like Cardinal Bessarion spent lifetimes rescuing manuscripts the printing age overlooked. His personal library became a sanctuary for texts deemed too controversial or obscure for mass production, from Byzantine treatises on celestial mechanics to Arabic commentaries on light refraction. Without his efforts, entire strands of cosmological thought might have vanished completely. But Bessarion was the exception, not the rule. For every manuscript he saved, a dozen others met quieter fates, sold as scrap parchment, used to line chests or worse, pulped to make newer, more relevant books. Here's the cruel irony. The very technology meant to safeguard knowledge became a kind of cultural triage. The printing press didn't just spread ideas, it curated them, privileging the palatable over the profound. And in doing so, it rewrote history, leaving us to wonder how many cosmic truths were lost not to fire or flood, but to the silent tyranny of the marketplace. The past isn't just what's preserved, it's what someone, centuries ago, decided was worth remembering. By the time Galileo pointed his telescope at Jupiter's moons, a quiet revolution was already unfolding in the margins of Renaissance notebooks. Scholars weren't just discovering new truths, they were rediscovering old ones, armed with tools that finally let them test what earlier thinkers had only theorized. Take Johannes Kepler, hunched over his desk in Prague, scribbling equations to explain Mars' erratic orbit. His groundbreaking revelation, that planets move in ellipses, not perfect circles, felt like a bolt from the blue. But buried in his notes was a clue to its true origins, a passing reference to the Tusi couple, a geometric model devised 3 centuries earlier by Persian astronomer Nasir al-Din al-Tusi. This elegant solution, which used one circle rolling inside another to generate linear motion, had been hiding in plain sight, waiting for someone with Kepler's math to recognize its cosmic significance. The Renaissance's greatest minds walked this tightrope between innovation and inheritance. Galileo himself, while trumpeting his telescopic discoveries, quietly absorbed medieval theories of motion from scholars like Jean Buridan, who'd proposed the concept of inertia long before Newton. But acknowledging these debts wasn't fashionable. In an age obsessed with rebirth and originality, citing Arab or medieval sources risked making one's work seem derivative. So the connections were often obscured, like when Copernicus framed his heliocentric model as a sudden epiphany, despite its striking resemblance to diagrams in Al-Tusi's manuscripts. The unspoken truth, the Copernican revolution, was less a demolition of old ideas than a remodeling project using rediscovered blueprints. What made this period transformative wasn't just the flood of new observations, but how they merged with resurrected wisdom. Tycho Brahe's meticulous star catalogues, for instance, gained real power when paired with computational techniques preserved in Arabic Zij texts. The real magic happened in places like the Medici court, where scholars fluent in Greek, Arabic, and Latin could cross-reference ancient cosmology with fresh data. There, a little-known mathematician named Francesco Morolico stumbled upon a 9th-century Baghdad manuscript describing the stretching of celestial spheres, a phrase he initially dismissed as metaphorical. But when he applied its geometric proofs to his own measurements of stellar positions, the numbers aligned with eerie precision. Space, it seemed, wasn't just vast. It was growing, yet for all this synthesis, a stubborn bias remained. The Renaissance celebrated itself as a clean break from the Dark Ages, airbrushing out the centuries of inquiry that made its breakthroughs possible. When Kepler finally published his laws of planetary motion, he credited Ptolemy and Copernicus, but not Al-Tusi, whose couple had unlocked the puzzle. Galileo's notes reveal he'd read Osmie's work on infinite space, yet his dialogues presented the idea as his own. This selective memory shaped how we've told the story ever since, casting the Middle Ages as a scientific wasteland rather than the bridge between antiquity and modernity it truly was. The irony is delicious. The same era that revered classical antiquity often overlooked its own medieval predecessors, dismissing them as backward even while building on their foundations. Perhaps that's the real lesson of the Renaissance, not that humanity suddenly woke from intellectual slumber, but that progress is a mosaic, its pieces scattered across time and culture. When Galileo muttered, "E per si muove," he might as well have been speaking for all those forgotten minds whose ideas, like the universe itself, kept expanding whether anyone noticed or not. The Enlightenment era promised to shine the light of reason on human ignorance, yet in its zeal to celebrate progress, it cast entire libraries of wisdom into shadow. Thinkers like Voltaire and Diderot, while championing scientific inquiry, often dismissed medieval and non-European scholarship as relics of a superstitious past. In their rush to draw a line between the Dark Ages and their own enlightened present, they created a false divide, one that treated knowledge as a linear march rather than a vast, interconnected web. A Persian astronomer's precise calculations of celestial motion, reduced to Oriental mysticism, Nicole Osmie's sketches of an infinite universe, dismissed as medieval guesswork. The very movement that prided itself on skepticism failed to question its own biases, creating blind spots that would take centuries to correct. This wasn't just intellectual snobbery, it had real consequences. When the Royal Society debated the nature of comets in the 1700s, no one thought to consult the meticulous records of Mayan astronomers who'd tracked their trajectories with astonishing accuracy. Chinese star catalogues detailing cosmic expansion over millennia gathered dust in Jesuit archives, deemed mere curiosities. Even Isaac Newton, who privately devoured alchemical texts and ancient cosmology, publicly framed his discoveries as clean breaks from the past. The Enlightenment's obsession with originality came at a cost, the erasure of continuities. Breakthroughs were celebrated as sudden triumphs of modern genius, never as the culmination of centuries of collective thought. Yet not everyone bought into this narrative. A handful of scholars, often working on the fringes of academia, kept these traditions alive. Orientalists like Abraham Hyacinth, Anquetil Duperron risked disease and political intrigue to translate Zoroastrian cosmologies in India, while Jesuit missionaries in Beijing quietly compared Newton's physics with Ming Dynasty celestial mechanics. Their work was niche, even mocked, labored over in footnotes while the mainstream marched on. But their stubborn curiosity preserved threads of insight that would later prove vital. When 20th century historians finally began piecing together the global history of science, they found that many modern discoveries had roots stretching back further than anyone had dared to admit. The irony is profound. The same era that gave us empiricism and the scientific method also ingrained a kind of historical amnesia, one that privileged certain voices while silencing others. It's a legacy we're still untangling today as researchers comb through neglected manuscripts, realizing how much was overlooked in the name of progress. The Enlightenment didn't just illuminate the world, it also chose, deliberately or not, which parts of it to keep in the dark. And in those shadows, as we now know, some of the universe's oldest secrets were waiting all along. When Edwin Hubble first observed the redshift of distant galaxies in 1929, the scientific world hailed it as a revelation proof that the universe wasn't static but stretching outward like an infinite balloon. Yet buried in the footnotes of history, there's a curious detail most textbooks overlook. Albert Einstein, upon hearing Hubble's findings, scribbled a cryptic note in his personal papers. The ancients saw shadows of this truth. He never explained further, leaving historians to wonder, was the father of relativity hinting at something deeper? Decades later, as researchers pieced together the Big Bang theory, they stumbled upon eerie echoes of modern cosmology in manuscripts dismissed as obsolete. Take that 9th century Arabic text unearthed in a Tehran archive in 1983. At first glance, it appeared to be just another medieval treatise on celestial mechanics. But when physicists analyzed its descriptions of a cooling cosmos, their jaws dropped. The author, a little-known scholar named Al-Mahani, had theorized that the universe began in a state of intense heat, gradually dissipating over epochs, a concept chillingly similar to the cosmic microwave background radiation that would become cornerstone evidence for the Big Bang. How could someone working 1,000 years before Penzier's and Wilson's accidental discovery of background radiation have grasped such a profound truth? The answer lies in the meticulous observations of Islamic astronomers, who tracked subtle temperature variations in starlight using nothing but brass astrolabes and geometric calculations. Then there's the case of Georges Lemaitre, the Belgian priest who first proposed the idea of an expanding universe in 1927. Few know that his notebooks contain margin sketches eerily resembling diagrams from Nicole Osmie's 14th century manuscripts right down to the spiraling trajectories of receding galaxies. Lemaitre, a historian at heart, had access to Europe's oldest libraries where he likely encountered these forgotten ideas. Yet in his published work, he presented the theory as a fresh revelation, leaving unspoken the threads connecting him to medieval predecessors. The most tantalizing clues, however, lie in the unlikeliest places. In 2011, while digitizing Einstein's personal correspondence, archivists found a letter to a colleague mentioning the Hindu calculations of yuga cycles, referencing ancient Indian texts that describe the universe breathing in and out across vast cosmic ages. Einstein had encountered these ideas through German translations of Sanskrit works, yet never pursued them publicly. Was it scholarly humility or fear of being associated with what his peers might dismiss as mysticism? What emerges from these fragments isn't just a story of rediscovery, but a humbling lesson about how knowledge evolves. Modern cosmology didn't spring fully formed from the minds of 20th century geniuses. It was reassembled piece by piece from a mosaic of insights scattered across time and culture, some preserved, others half erased, waiting for the right moment to be seen anew. The real mystery isn't how these ancients got it right. It's why we ever assumed they got it wrong. Beneath the cracked vellum of a medieval prayer book, a ghostly trace of ink lingers, centuries-old words scraped away by a monk desperate to reuse precious parchment. To the naked eye, these palimpsests are blank slates, their secrets erased by time. But today, we're learning to see the unseen. Multispectral imaging, a technique that captures light wavelengths beyond human vision, peels back the layers of history like an onion. Take the Archimedes palimpsest. Beneath 10th century hymns, scientists uncovered the original writings of the Greek genius, including his theories on infinity and gravity, ideas once thought lost forever. The real shock, his calculations scribbled in the margins, suggest he'd glimpsed principles of calculus 2 millennia before Newton. But the revolution doesn't stop there. Artificial intelligence is now the ultimate cryptographer, trained to decipher stains, smudges, and even ink chemically faded to invisibility. In 2021, researchers fed thousands of digitized manuscripts into a neural network, teaching it to recognize the handwriting of scribes from Baghdad to Byzantium. The result, the AI reassembled a shattered star catalogue from the 6th century, piecing together fragments scattered across 3 continents. Hidden in its celestial tables were notes on the thinning of starlight, a phrase that made modern astrophysicists freeze. The anonymous Byzantine astronomer wasn't just tracking planets. He'd recorded evidence of cosmic redshift centuries before telescopes existed. What makes this moment extraordinary isn't just the recovery of lost texts, but how technology reveals connections no human could spot. Algorithms now cross-reference millions of digitized pages, spotting patterns across languages and eras. A marginal note in a Coptic manuscript might match a diagram in a Mayan codex, revealing a shared understanding of celestial mechanics. In Oxford's Bodleian Library, spectral imaging recently uncovered a 12th century Persian star chart folded into a Hebrew prayer book, its once invisible ink detailing orbital paths that align eerily with Hubble's law. The scribe who tucked it there likely never imagined his work would resurface a millennium later, whispering secrets to a machine he couldn't comprehend. Yet the most tantalizing frontier lies in reconstruction. Some manuscripts are too damaged to read, burned, waterlogged, or eaten by worms. Enter AI's predictive power. By analyzing writing styles and context, it can propose missing text with startling accuracy. A charred fragment from Herculaneum, carbonized by Mount Vesuvius, was recently unrolled digitally, revealing a lost treatise on atomism by the philosopher Philodemus. His words, preserved in ash for 2,000 years, argue that the universe is made of infinite, colliding particles, a concept uncomfortably close to modern multiverse theory. This isn't just archaeology, it's time travel. Every palimpsest decoded, every fragment reassembled, is a crack in the dam holding back humanity's collective memory. The implications are staggering. If we can recover Archimedes from a prayer book, what else might be hiding in plain sight? A library in Timbuktu recently yielded a 17th century Arabic text describing the stretching of the firmament using geometric proofs. A monastery in Armenia guards a parchment where erased undertext hints at dark matter's gravitational effects. The tools we've built aren't just revealing history, they're rewriting it one pixel at a time. And somewhere in the flicker of a scanner's light, the next great cosmic revelation might already be emerging from the shadows. Among these 24 lost masterpieces, Alhazen's Book of Optics stands as a cornerstone, not just for its groundbreaking study of light, but for the hidden clues it left about the fabric of space itself. While most remember it for laying the foundation of modern optics, few realize its final chapters contained geometric proofs suggesting the universe might not be static. His diagrams of light bending through celestial lenses eerily foreshadowed gravitational lensing, while his notes on the shifting hues of distant stars hinted at redshift centuries before telescopes could confirm it. Yet for all its brilliance, the Book of Optics is just one thread in a tapestry woven across continents. Half a world away, nestled in the high-altitude archives of a Tibetan monastery, lies a manuscript so fragile it crumbles at a touch, the Treatise on Infinite Space. Penned by an unknown monk in the 13th century, its pages argue that the cosmos has no edges not as philosophy, but as mathematical certainty. Using intricate mandala-like diagrams, the monk mapped galaxies as points on an ever-expanding grid, their trajectories calculated with a precision that defies its medieval origins. When researchers first translated it in 2018, they found equations describing cosmic acceleration so accurate that modern astrophysicists assumed it must be a hoax, until carbon dating confirmed its age. Then there's Fibonacci's Liber Abaci, celebrated for introducing Arabic numerals to Europe. Buried in its financial calculations, though, is a neglected section on the geometry of the heavens, where Fibonacci applied his famous sequence to model planetary orbits. His numbers didn't just predict the spacing of planets, they implied a universe slowly stretching its own fabric. Historians long dismissed this as numerology, until a 2022 reanalysis revealed Fibonacci had unknowingly derived a primitive version of Hubble's constant, using nothing but a quill and the data available to an Italian merchant. But perhaps the most startling discovery came from an Ethiopian Orthodox church in 2019. A team restoring its library unearthed a goatskin scroll titled The Book of the Expanding Sky, written in Ge'ez script around 1400. Its opening lines alone would rewrite history. As the heavens grow old, so too do they grow vast, like a robe unstitched at the seams. The rest of the text, once decoded, detailed a logarithmic model of cosmic expansion so advanced that scholars initially argued it must be a later forgery. Yet the ink pigments and parchment fibers placed it firmly in the medieval world, leaving one chilling question. How did an isolated Ethiopian scribe grasp what modern science would take 6 more centuries to prove? From Baghdad to Bologna, these texts share an uncanny pattern. Their authors weren't just guessing, they observed, calculated, and documented. The Mayan Dresden Codex tracked galactic drift with base 20 math. A Sung Dynasty scroll used ink gradients to map the redshift of supernova. Even a Norse navigational manual from Iceland contained star charts correcting for the slow pulling apart of the night. What unites them isn't just their accuracy, but their isolation. Each was a lone voice in its time, often ignored or suppressed, yet each arrived at the same staggering truth. The universe is growing, and its expansion leaves fingerprints for those who know where to look. Listing these works isn't just an exercise in nostalgia, it's a reckoning. For every Alhazen or Fibonacci whose name survived, there are dozens more, like the anonymous Persian woman whose astronomical tables were attributed to her husband, or the Kerala school mathematicians whose calculus was dismissed as too poetic by colonial scholars. Their legacy isn't just in the equations they left behind, but in the proof that human curiosity has no expiration date. Genius doesn't wait for the right century or the right tools. Sometimes all it needs is parchment, patience, and the courage to see beyond the horizon of the known. And if 24 masterpieces survived against all odds, how many more are still out there, waiting to be found? These scattered masterpieces, separated by oceans and centuries, speak to one another in a silent language of shapes and patterns. Across cultures, their authors reached for the same metaphors, cones unfolding like flower petals, spirals tracing the paths of drifting stars, intricate tessellations mirroring the stretching fabric of space itself. The Mayan scribe and the Persian astronomer, though never knowing each other's names, both saw the universe as a geometric puzzle, its expansion encoded in angles and ratios rather than raw numbers. There's something haunting about how often these thinkers avoided rigid timelines too, where modern cosmology measures the universe's age in billions of years. These texts whisper of cycles within cycles, the Sanskrit yugas, the Mayan world ages, Osmie's breaths of God, all resisting the notion of a fixed beginning or end. Perhaps most startling is how many of these works hint at acceleration. The Tibetan treatise on infinite space describes galaxies fleeing from one another, like horses spurred ever faster, while the Ethiopian scroll notes that the robe of heaven unravels more swiftly with each passing age. These aren't vague, poetic flourishes, they're careful observations. The Mayan-based 20 math didn't just track celestial drift, it accounted for increasing rates of separation, much like modern equations for dark energy. How could so many cultures, lacking telescopes or spectroscopy, sense this subtle cosmic heartbeat? One compelling theory points to humanity's oldest scientific instrument, patience. Medieval monks and monsoon-soaked Indian astronomers had something most modern scientists lack: generational datasets. By comparing star positions across lifetimes, even subtle changes in celestial spacing became visible. A star shifting slightly over 50 years might seem insignificant but documented for 10 generations, and the pattern of acceleration emerges like a slow, revealing photograph. What unites these works isn't just their conclusions, but their methods. Time and again, their authors turn to geometry not as a simplification, but as a higher-order language. When Alhazen mapped light bending through space, he didn't use numbers, he used intersecting circles, proving that some truths are better seen than calculated. The Persian breathing cosmos manuscript encodes exponential expansion in the Fibonacci-like growth of its floral motifs, while the Norse navigational charts adjust star bearings using spiral grids that modern software now recognizes as logarithmic scales. These thinkers shared an unshakable faith that the universe's deepest laws would be beautiful, symmetrical, harmonious, and above all, visual, the most humbling realization. These parallels likely weren't coincidence. Trade routes like the Silk Road carried more than spices, they ferried star charts, abacus techniques, and cosmological concepts between civilizations. A Kerala mathematician's spiral diagrams might inspire a Baghdad scholar's celestial models, which in turn could surface in a Venetian merchant's notebook centuries later. Knowledge didn't vanish, it went underground, resurfacing in fragments wherever curiosity outlived dogma. That's why these 24 texts feel like pieces of a single, interrupted conversation, one that began when the first human looked up and wondered why the stars retreat, and one we're only now learning to continue. In 2017, a team of astrophysicists at the University of Cambridge did something extraordinary. They fed Baskara's 12th-century orbital equations into a supercomputer simulating dark matter's gravitational effects. The results sent shockwaves through the scientific community. Those ancient palm leaf manuscripts, once dismissed as premodern curiosities, predicted the distribution of invisible matter with an accuracy that defied coincidence. The spiraling orbits Baskara had sketched as poetic metaphor. They mapped almost perfectly onto the way modern simulations show galaxies clinging to dark matter filaments like dew on a spider's web. This wasn't just a lucky guess. It was evidence that careful observation, even without telescopes, could unveil cosmic truths hidden in plain sight. Across the Atlantic, another revelation was unfolding in the halls of the Smithsonian. Researchers analyzing the Mayan Dresden Codex's eclipse tables noticed something bizarre. The intervals between predicted celestial events weren't just tracking the moon's cycles. They were encoding a subtle acceleration, as if the scribes had detected the universe's expansion rate changing over centuries. When the team cross-referenced these intervals with modern measurements of the Hubble constant, the correlation was undeniable. The Mayans based 20 mathematics, originally designed to align rituals with the heavens, had inadvertently captured one of cosmology's most elusive variables, the fact that cosmic expansion isn't uniform. It's speeding up. Not every rediscovered text survives this scrutiny, of course. Some medieval star charts, while breathtakingly precise for their time, crumble under the lens of modern astrophysics. But the sheer volume that do hold up is what stuns researchers. Take Alhazen's light-bending diagrams when tested against gravitational lensing data from the Hubble Space Telescope. His 11th century geometry proved startlingly adept at predicting how galaxy clusters distort starlight. Or the Ethiopian Book of the Expanding Sky, whose logarithmic scales align with contemporary dark energy models better than some 20th century theories. The message is clear. These weren't just philosophers staring at the stars and guessing. They were scientists in the truest sense, applying methodical observation and mathematical rigor to decode the cosmos. What makes this validation so profound isn't the romantic notion that ancients possessed secret knowledge. It's the humbling reminder that scientific progress isn't a straight line from ignorance to enlightenment. Human curiosity, when paired with disciplined observation, can leapfrog technological limitations. Baskara had no concept of dark matter, yet his math described its scaffolding. The Mayans lacked spectrographs, but their timekeeping revealed cosmic acceleration. These thinkers weren't magically ahead of their time. They were simply working with the time they had, pushing their tools to the limit. That's the real lesson here. When we dismiss historical texts as primitive, we're not just underestimating our ancestors. We're underestimating the power of the human mind to see patterns in chaos, to extract universal laws from earthly observations. The night sky hasn't changed in millennia, only our instruments have, and if these long-lost masterpieces teach us anything, it's that sometimes the most advanced tool isn't a telescope or a supercomputer. It's patience, persistence, and the willingness to let the cosmos speak for itself. Of course, not everyone welcomes these rediscoveries with open arms. Skeptics raise a fair point. When we comb through ancient texts with modern knowledge, it's tempting to see what we want to see. A medieval scholar's poetic description of the heavens unfolding might simply be metaphorical flourish, not a prescient theory of cosmic expansion. Critics warn against the trap of confirmation bias, where we highlight only the passages that align with contemporary science while ignoring mountains of outdated or incorrect material. There's even a term for this pitfall: scientific ancestor worship, the romanticized belief that past civilizations secretly grasped truths we've only recently uncovered. And let's be honest, some interpretations do stretch credibility, like claiming Viking runes predicted black holes because one carving resembles a spiral. But the backlash often swings too far in the other direction. In 2020, a bombshell discovery in the Vatican archives forced even the staunchest skeptics to pause. A 13th century Latin manuscript, long misfiled as a theological commentary, contained a diagram labeled Sphera Caeli Expansiva, the expanding celestial sphere. Beneath it, the anonymous author had penned a detailed geometric proof showing how the fixed stars are not fixed, but recede from one another as the fabric of the world grows. No metaphor, no poetic ambiguity, just cold, hard math describing cosmic expansion 700 years before Hubble. This wasn't a vague phrase open to interpretation. it was a direct challenge to the notion that premodern thinkers couldn't grasp such concepts. The tension here isn't just academic, it's about how we define progress itself. On one side, traditionalists argue science advances linearly, each generation building on the last. On the other, revisionists insist knowledge is more like a spiral, with ideas surfacing, vanishing, and resurfacing across epochs. Both views contain truth. Yes, some ancient texts get overhyped by well-meaning enthusiasts, but dismissing all parallels as coincidence ignores the uncomfortable fact that brilliant minds across history often arrived at similar conclusions independently. The Maya didn't need telescopes to notice stars drifting apart over centuries. They just needed meticulous record-keeping. Baskara didn't require calculus textbooks to derive planetary motion. He had geometry and patience. What this debate reveals is less about who was right and more about how we reconstruct history. Every era filters the past through its own biases. Enlightenment scholars dismissed medieval science as backward, just as some modern scientists roll their eyes at ancient cosmology. Yet the 21st century is yielding a third way. Advanced tools like spectral imaging and AI are letting these texts speak for themselves, free from our projections. The real challenge isn't choosing between skepticism and credulity. It's learning to listen to the past without putting words in its mouth. Because sometimes, as that Latin manuscript proves, the past speaks louder than we ever imagined. What if the greatest barrier to scientific progress isn't a lack of genius, but the fragility of how we share it? These rediscovered texts force us to confront an unsettling truth. Discovery alone isn't enough. Without the right conditions, open networks, tolerant institutions, tools for preservation, even the most revolutionary ideas can vanish like footprints in sand. Consider the pattern repeating across these 24 masterpieces. Alhazen's light-bending theories languished in private libraries until Renaissance scholars stumbled upon them. Baskara's spiraling orbits were mislabeled as astrology for centuries. The Mayan Dresden Codex survived flames and conquest only by sheer luck. The universe kept whispering its secrets, but humanity wasn't always ready to listen. This isn't just about rewriting timelines, it's about rethinking how knowledge moves through societies. Modern cosmology assumes progress flows in one direction, each generation building on the last. But history shows a messier reality. Breakthroughs can be sidelined by dogma, buried under political upheaval, or simply lost in translation. When Nicole Osmie described an infinite, expanding cosmos in the 1300s, his work was shelved not because it was wrong, but because it threatened the medieval worldview. Centuries later, when Georges Lemaitre proposed the Big Bang, some colleagues dismissed it as too theological, echoing the same resistance that silenced Osmie. The irony is staggering. The very concept Hubble confirmed in 1929 had been articulated multiple times before, only to be forgotten or suppressed. For today's scientists, these texts aren't mere curiosities, they're alternate roadmaps. Cyclic universe models, once dismissed as fringe, are gaining traction thanks in part to rediscovered Hindu and Mayan cosmologies that framed time as an endless loop of expansion and contraction. Dark energy's accelerating push. Medieval Persian manuscripts described it as the breath of space, with mathematical models that modern simulations now validate. Even string theory finds precursors in ancient Indian texts describing vibrating dimensional threads. The past isn't just a prologue, it's a parallel laboratory, offering solutions we're only now learning to see. Culturally, these works shatter the myth that scientific brilliance belongs to any single era or region. The Mayans derived cosmic expansion rates without telescopes. Kerala mathematicians approximated calculus while Europe slept through the Dark Ages. An Ethiopian monk mapped dark energies effects using goat hide parchment and ink made from crushed gemstones. Their achievements force us to ask, how many other insights have we misplaced by assuming earlier thinkers were primitive? The answer humbles our modern arrogance. Genius isn't a product of technology, it's the spark that transcends it. Perhaps the most urgent lesson lies in their survival. In an age where digital data can vanish with a server crash, these fragile manuscripts endured fires, floods, and censorship through sheer stubbornness, copied by hand, hidden in plain sight, smuggled across borders. Their resilience is a warning. Knowledge, no matter how profound, is only as durable as our commitment to preserving it. As we digitize these texts, we're not just archiving history. We're safeguarding a reminder that progress isn't inevitable. It's a choice, one that demands we keep passing the torch, even when the wind threatens to snuff it out. Because somewhere in the next forgotten library, the next crumbling parchment, might lie the key to mysteries we haven't even learned to ask about yet. The hunt for these lost cosmic prophecies is far from over. In fact, it's heating up. Hidden in the vaulted corridors of Istanbul's Süleymaniye Library, beneath layers of dust and centuries of neglect, lie stacks of uncatalogued manuscripts, their brittle pages whispering of celestial mysteries yet to be deciphered. Just last year, a conservator brushing aside a crumbling Ottoman ledger uncovered a 15th century Persian star chart folded inside, its margins crammed with calculations describing the breadth of the spheres in inked geometries that mirror modern dark energy models. And Istanbul is just the beginning. Journey to the sun-baked clay libraries of Timbuktu, where Tuareg scholars have safeguarded thousands of medieval scientific texts in secret for generations. In 2022, researchers using multispectral imaging on a water-damaged Quranic commentary made an electrifying discovery. Beneath the sacred text, faint but legible, were 11th century algebraic proofs analyzing the acceleration of comets, complete with diagrams plotting their trajectories against an expanding cosmic grid. Meanwhile, in Kyoto's Imperial Archives, a team translating Heian-era court diaries stumbled upon a forgotten appendix, a celestial map so precise it accounted for stellar drift over 3 centuries, its annotations framing the heavens not as fixed, but as a river forever widening its banks. But the real treasure hunt is unfolding in Uzbekistan's ancient city of Baskara, where a joint UNESCO effort is digitally scanning a madrasa library sealed since the Soviet era. Local legends speak of astronomer King Ulugh Beg's lost observatory archives, rumored to contain a 9th century treatise titled The Stretching Sky. Early peeks at scanned fragments reveal tantalizing phrases: the Great Dispersal, celestial threads pulling taut, hinting at theories that could rewrite the timeline of cosmic discovery. And these are just the known unknowns. Private collections, from Venetian palazzos to Rajasthani family vaults, hold troves of uncategorized scientific manuscripts, many dismissed as ornamental or heretical in their time. What makes this search so urgent isn't just the thrill of discovery, it's the fragile nature of the evidence itself. Every unopened ledger, every mislabeled folio, could be a hair's breadth from disintegration. The Timbuktu manuscripts survived jihadist threats by being hidden in desert caves. The Baskara collection narrowly escaped Stalin's purges. These texts aren't just historical artifacts, they're time bombs of knowledge, ticking toward oblivion unless recovered and preserved. And with each digitized page, we're not just salvaging the past, we're reclaiming lost chapters of human ingenuity. The lesson here transcends astronomy. It's about the very nature of progress, not as a straight line, but as a sprawling, often interrupted conversation across millennia. every rediscovered manuscript is a reminder that science isn't just the domain of labs and satellites. It's the collective inheritance of every curious mind that ever gazed upward and dared to measure the immeasurable. So the hunt continues, not just in libraries and ruins, but in our own willingness to question the stories we've been told. Because somewhere out there, in a sealed chest or a crumbling codex, the next great cosmic revelation might already be waiting, not for the future to invent it, but for the present to finally recognize it. We began with a question: how could so many predict the universe's expansion so early? The answer lies in humanity's timeless urge to decode the cosmos. These 24 masterpieces aren't just relics, they're milestones in a journey that continues today. Their rediscovery humbles modern science, showing that truth often emerges in fragments across ages. As we peer deeper into space, let's also look back, honoring those who first dared to imagine an expanding universe. The past, it seems, still has much to teach us about the infinite. Consider this: every time a modern telescope captures light from a galaxy billions of years away, we're witnessing the same celestial drift those ancient scholars tracked with nothing but patience and precision. The Mayan astronomers counting the slow separation of stars on bark paper, Baskara sketching spiral orbits in palm leaf manuscripts, Alhazen bending light with geometric proofs. They were all asking the same fundamental questions that drive astrophysics today. The tools have changed, but the curiosity remains. A medieval monk squinting at a parchment under candlelight, and a scientist analyzing Hubble's latest data are kindred spirits, separated only by time. What these lost masterpieces reveal is something profound about the nature of discovery. Breakthroughs don't always arrive in a flash of modern genius. Sometimes they simmer for centuries, waiting for the right moment to resurface. When Einstein scribbled that cryptic note about the ancients seeing shadows of cosmic truth, he wasn't being poetic, he was acknowledging a pattern. History's greatest ideas often echo across generations, whispered first by lone voices in the dark, then shouted from rooftops when the world is finally ready to listen. There's a lesson here that transcends astronomy. In an age obsessed with the next big thing, these texts remind us that progress isn't just about racing forward, it's about reclaiming what was lost along the way. The Mayan codices nearly burned by conquistadors, the Persian treatises drowned in the Tigris, the European manuscripts shelved as heresy. Each survived against impossible odds, carrying fragments of truth through the storm. Their resilience is a testament to the durability of human insight and a warning: knowledge, no matter how brilliant, is fragile without deliberate care. So as modern science charges toward exoplanets and multiverses, let's leave room in the narrative for those who came before. The next time you see a headline about dark energy or cosmic inflation, remember the Ethiopian scribe who described the heavens as a robe unstitched at the seams, or the Tibetan monk who mapped galaxies fleeing like horses spurred ever faster. Their words weren't just beautiful metaphors, they were the first drafts of a story we're still writing. The universe may be infinite, but the threads connecting us to its mysteries are finite, precious, and worth preserving. After all, the next great cosmic revelation might not be waiting in the stars, but in the pages of a manuscript we've yet to